Hi there, this is Heath. This is section 12.5 on lines and planes in 3 dimensions. Let's get started. In 2 dimensions, we use the equation y equals mx plus b to represent a line segment. The value of m told us the direction that the line segment pointed, and the value of b told us where to position the line segment relative to the origin. The higher b was, we anchored it to the y-axis at that point. We can't use this form of the equation in 3 dimensions because we need to describe a third variable z. But we're still going to make use of the idea that a line has to have a direction and a position. Those two things are going to be important. So let's look at a couple of examples. If we have a line that goes to the point x naught, y naught, z naught, and so that's got to be some point on the line. That's going to be our position. And it's parallel to a vector that points in the direction v1, v2, v3. Then here's how this equation works, is that I can take this vector and multiply it by any constant. I'm going to call this constant t for right now. And that changes the size of the vector, makes it larger or smaller. And if I add this scaled version of that vector to this point, and I can scale it by negative amount also, then for every value of t, I generate a new point on this line. And eventually the entire line gets generated by replacing t with the all real numbers. And so that's that way this works. The only difference here is that p is a point, and I want, since v is a vector, I have to add vectors together. And so r naught is a vector whose coordinates are the same as the coordinates of p. So if p has the point x naught, y naught, z naught, then r naught is the vector x naught, y naught, z naught. We call this a position vector. Okay? So what we'll do is we'll take the position vector as a starting point, take the direction vector, scale it by all real numbers, and add that to the position vector. Okay? So when we do that, we get for the line that the line is the vector, the equation xyz is equal to the position x naught, y naught, z naught, plus the vector, the direction vector, v1, v2, v3, scaled by our scaling factor, t. If we add these together, this is the same thing as x naught plus t times v1, y naught plus t times v2, comma, z naught plus t times v3. And so if I just, instead of writing this as a vector, I just write the individual components. X is equal to this, y is equal to this, z is equal to this. We call these the parametric equations for the line. We have both forms. We have the vector equation, which combines all three coordinates into a single vector equation. And then we have the parametric equations, which separates them out into three separate equations. So the vector equation is combined. The parametric equations are separated. But they work the same way. So here's an example. Let's find parametric equations for the line that starts at the point -2, 0, and 4, and it goes parallel to the vector 2i plus 4j plus -2k. Okay? So the idea is that the x-coordinate and the y-coordinate and the z-coordinate will start at its starting points, -2, 0, and 4. Those points stay fixed, but the amount that we add to it changes depending on how far away we want to move from this point. And we can scale these values by t. So 2t and 4t and -2t. That gives us parametric equations for the line. The position stands by itself. The direction takes a variable. I've got this typed up on the next slide. Parametric equations require one equation for each dimension. This example is in 3 dimensions, so we need 3 equations. In each equation, the coordinate from the point -2, 0, 4 is a constant term, while the coordinate from the vector 2i plus 4j minus 2k gets multiplied by t. And so we get -2 plus 2t. 0 plus 4t is just 4t, and then 4 minus 2t. This is what we had back here. This is the same answer. Okay? So if we know a point and we know a direction, it's very easy to write parametric equations. If we want the vector equation, we just combine all of this into a vector on each side. On the left side, we just get x, y, z. And on the right side, we get -2 plus 2t, 4t, and 4 minus 2t. These carry exactly the same information. They're just written as 3 separate equations versus one single equation. Both of these are correct ways of writing a line. The problem just in this case asked for parametric equations. All right. Let's try another one. Find parametric equations for the line that goes through this point and this point. So P is the point -3 to -3, and Q is the point 1, -1, 4. So we have 2 points, but what do we need? We need a point and a vector. The vector has to tell us the direction of the line. And so for the vector, we're going to use the vector that goes from P to Q. So we start at -3 and end at 1. That's 4 units forward. -3 units start at 2, -1 ends at -1. That's 3 units backwards, so -3. And -3 to 4 is 7. This vector is going to get multiplied by t and then added to our starting point. Okay? So in this example, we have 2 points, but we're not given a vector. We generate a vector to use for the line by calculating PQ, which is the same thing as Q minus P, which is 4, -3, 7. Since the line that goes in this direction through P, this is, let me draw you a picture here. I have 2 points on this line. The line that goes in this direction and starts at P is exactly the same line as the line that starts at this point and goes in this direction. And so we can actually use either P or Q to generate the parametric equations, even though we used P as the starting point of the vector. And therefore, either of these answers is correct. We can use the 4 and -3 and 7 and add it to the coordinates of P, or we can use the 4 and the -3 and the 7 and add to the coordinates of Q. Okay? Both of these answers are correct. All right. Let's look at another example. A helicopter is about to fly directly from a helipad at the origin. So here's our origin, here's our helicopter. I can't draw, but that's our helicopter and its little tail. There you go. In the direction of the point 263. So there's 26. I'm going to go up 3 units from there. So the helicopter is going to fly in this direction at a speed of 63 feet per second. What is the position of the helicopter after 10 seconds? Okay. So the first calculation is easy. Since we traveled at 63 feet per second for 10 seconds, the total distance is 630 feet. So then we want to know how many feet it is from the origin to this point, 263. Going from the origin to 263, we use the distance formula, or the Pythagorean theorem, if you want to think of it that way. And we get the square root of 2 squared plus 6 squared plus 3 squared equals 7 feet. So this is 7 feet long. And the helicopter traveled total of 630 feet. Well, that's 90 times as far as this one vector here. And so we need to go to the point that's 90 times further away than 263. And that's 180, 540, and 270. And so that's the final position of the helicopter. 180, 540, and 270. Okay? Excuse me. We find the distance that the helicopter traveled. We find out how many times that is bigger than the point 263, the vector 263. And then, since that's 90 times further, we have to scale by a factor of 90. Okay? All right. So let's say we have this line L, and we know how to write equations for that line now. And we have this point S, and we want to find the distance from the point to the line. Well, the distance is the shortest distance, which is the distance that would form a right triangle here. Okay? And there are a couple of ways of calculating this distance. If we knew what this point here was, we could just use the distance formula. But the chances are we don't know what this point is. But we do know a point on the line, because the equations of the line have a starting point built into them. And no matter where that point is on the line, I can build the vector from P to S, and I can find the projection of this vector onto L. And the projection will be this vector. The projection of vector V onto vector L, onto line L. And now I have the hypotenuse and one leg of a right triangle, and the distance is the other leg. So the vector from P to S and the projection of PS onto L are two legs of a right triangle, and the third leg is the distance we want. And we can use the Pythagorean theorem at that point. So let's try this problem. We want to find the distance from the point 115 to the line x equals 1 plus t, y equals 3 minus t, and z is equal to 2t. And so this line was built using the point 1, 3, 0, and using the vector 1, -1, and 2. Now, it would be very lucky for us if that point were right here, but chances are it's not. It's probably somewhere else. And so this vector will not capture the distance that we want. But the vector from this point P to the point S, if we start at 1 and end at 1, that vector is 0. If we start at 3 and end at 1, that's -2. And if we start at 0 and end at 5, that's 5. I'm starting at P and ending at S and generating this vector. And so what I want to do is I want to calculate the projection of this vector onto this vector. Okay? So we actually don't need the actual coordinates, we just need the size of the projection, which is the component projection or the scalar projection of 0, -2, 5 onto 1, -1, 2. And remember that this formula is the dot product of both vectors divided by the magnitude of the little vector, the one that is being projected onto. So the dot product of these two vectors is 0 plus 2 plus 10 is 12. And the magnitude of this vector is the square root of 1 plus 1 plus 4 is the square root of 6. And so this length here is 12 over square root of 6. And the hypotenuse here has a length, well, again, distance formula for this vector, 0 plus 2 squared plus 5 squared is 0 plus 4 plus 25. This side will be square root of 29. And so to find a third side, we use the Pythagorean theorem. The distance will be the square root of 12 over square root of 6 squared plus square root of 29 squared. And that turns out to be the square root of, not plus. I messed that up. Let me back up here. We add when we are adding legs. This is the hypotenuse. It's the square root of 29 squared minus one of the legs. Square root of minus 12 over the square root of 6 squared. There we go. That's better. And when we calculate that out, this turns out to be the square root of 5. Okay? Sorry about that. On the next couple of slides, we have these steps all written out, but I want to walk through these steps with you at first. We find the vector that generated the line. We find the vector that connects this point to the one we're given. That's the hypotenuse. Then we project the hypotenuse down onto the line to get the size of the leg. And then once we know the size of the hypotenuse and the size of the leg, we can find the size of the other leg. All right. So just summarizing here, the line is generated by this point in this vector. The vector that goes from P up to S has these coordinates, and the scalar projection of this vector onto this vector is the dot product over the magnitude of the vector that is being projected onto. So that's 12 over square root of 6. And the length of the vector v is the square root of 29. That's about 5.4. I don't know if we need that number yet. But then we used the Pythagorean theorem, 12 over root 6 squared plus d squared equals root 29 squared. And so the distance is the square root of this amount minus this amount, which is root 5. Okay? All right, let's move on. So summarizing, the distance from a point to a line, if we have a point on the line and S is any other point, we take the vector from P to S, that's the hypotenuse, and we square that. And then we take the leg of the triangle, which is the dot product of both of these vectors, divided by the magnitude of the vector we're projecting on. That's the scalar projection. We square that, and then we take the square root to get the distance. Okay? This just recaps everything we've been doing in example 4. All right, we've talked about lines for a while. Let's talk about planes. Okay? The equation for a plane also involves a position and a direction, but we got a small problem. There are lots and lots of directions that lie on the plane. And so we would not be able to get a good equation because knowing a direction doesn't tell me the shape of the rest of the plane. So instead what we're going to use is what's called the vector that points at a right angle to the plane. That's called the normal vector to the plane. Okay? We call that direction the normal direction to the plane. A vector that travels in that direction is called a normal vector. We learned last time how to create perpendicular vectors by taking the dot product. That is, if I find two vectors that are in the plane, and I take their cross product. I said dot product a moment ago. Cross product. Then we get the vector that's perpendicular to those. We'll use cross products in a moment to calculate normal vectors. So if a plane contains the point x naught, y naught, z naught, and it's normal to the vector ABC, then the left side of the equation is ax plus by plus cz. This side comes directly off of the normal vector. And the right side we get, it's going to be a constant. It's ABC times xyz, like a dot product. A times x naught plus b times y naught plus c times d naught. It's also what you would get if you just plugged in x naught, y naught, and z naught for x, y, and z and calculated it out. This will make a little more sense after we've done an example. But this is a constant, and there's a formula for the constant, but it's an easy formula. Let's try an example. Let's find an equation for the plane that contains the point negative 307 and is perpendicular to the vector (5), 2, and negative 1. Okay? So the left side of the equation is 5x plus 2y minus z. The left side of the equation uses the normal vector. And again, the normal vector is the perpendicular vector to the plane, or the orthogonal vector to the plane. So it uses the normal vector. There are actually two directions the normal vector can point. It can point above the plane or below the plane. You're allowed to use either one. It doesn't make a difference. Both answers will be correct. All right. So how do we find the right-hand side? The right-hand side is a constant, and it's the constant that has to work with this point. And so if I plugged in this point, 5 times negative 3 plus 2 times 0 minus 7, that's negative 15 plus 0 minus 7 is negative 22. Well, that's the constant that works when we plug in this point. And so we plug in the point to find the constant. Okay? All right. So here's the solution written out again. In 3 dimensions, a line has a separate equation for each variable, but a plane just has a single equation. The left side of the equation is given by the normal vector n, 5x plus 2y minus z. And then to find the constant on the right side of the equation, we plug in the point p naught, and that's where we get the negative 22 from. And so this is the answer that we get. All right. So let's keep going. Let's find an equation for the plane that contains these 3 points. 0, 0, 1, which is 1 unit up in the z direction. That's this point here. 2, 0, 0, which is 2 units out in the y direction. That's this point here. And 0, 3, 0. That's 3 units out in the z direction. That's this point here. Okay? So we're looking for the plane that contains these 3 points. This plane actually continues on in all directions. I've just shown the part where x and y or z are all positive. Okay? So we have 3 points. What we need is a point. We've got those, and a normal vector. We need the vector that forms a right angle with this plane. And we don't have that. So here's how we're going to get that. We're going to take 2 vectors on this triangle here and calculate their cross product. Okay? So it doesn't matter which 2 vectors we pick, but remember, these are points and not vectors. The vectors will be the vectors that go between the points. So we could choose, for example, we could choose BC, for example. And BC is the vector. If I start at 2 and end at 0, that's negative 2. Then 3, and then 0. And then we could choose the vector, say, AB. That's the vector 2, 0, and negative 1. And then we could calculate their cross product. Well, here's how we calculate cross products again. We did this last time, but we'll do this again. We write the vectors one above each other. When we calculate the x-coordinate, we ignore the x column. We multiply diagonal pairs and subtract. So -3 minus 0 is -3. All right. And then for the y-coordinate, we block out the y column. We multiply diagonal pairs and subtract. We get 2 minus 0, which would be 2, but we have to flip the sign of the middle coordinate. And then for the z-coordinate, we get 0 minus 6, which is -6. And this gives me a normal vector. Now, I got 3 negative coordinates because I calculated, it turns out, the normal vector that points on that side where everything's moving in the negative direction. If I want to, I can use the positive version of that vector also. If I want, I can use 3, 2, 6 instead, just to reduce the number of negative signs I have to deal with. But if I flip a sign, I have to flip all 3 of them. I have to make the entire vector the negative of what I had before. Okay? So I can use either of these 2 vectors. I'll go ahead and use the one with all the positive values. That tells me the left side of the equation. But it doesn't tell me the right side of the equation. For that, I need to plug in one of the points. Which point do I plug in? If you have done everything correctly up to this point, it doesn't matter. All 3 points will give us the same answer. If I plug in A, I will be plugging in 0, 0, 1, and I'll get 6 times 1, and that's 6. If I plug in B, I'll be plugging in 2, 0, 0, and 3 times 2 is 6. And if I plug in C, I get 0, 3, 0, and 0 plus 6 plus 0 is 6. And so all 3 points gave the same answer. That should be the case if you've done everything correctly. Okay? All right. So we're looking for a plane. Our answer will be a single equation. We're given 3 points, but we require a point in a normal vector. We can generate points by subtracting. In my example, I used BC. In this example, I'm using, this solution, I'm using AC. These are vectors that lie in the plane, so they're not normal vectors. So we now need to calculate a cross product. And when we calculate the cross product, this time we get the positive values, 3, 2, 6. And that gives us the left side. And then to find the constant term on the right side, we plug in any of the 3 points we were given. And that gives us 3x plus 2y plus 6z equals 6 for the answer. Okay? All right. Now we're looking at 2 planes here. This is hard for me to draw, so let me... Well, okay. That's sort of okay. L is the line where these 2 planes intersect. Okay. And the question is, if this is X and Y and Z, where does this point X, where does this line L cross through the YZ plane? If I extend L, where does it intersect through the YZ plane? Oh, wow. So how do we handle that? Okay. Well, if this line L if this point is on line L, then actually these planes will extend to include that point, because L is the intersection of those two planes. And so this point of intersection, let's call it P. P is on both planes and the YZ plane. And the YZ plane is important because what is the X coordinate if you're on the YZ plane? The X coordinate would be 0. A positive X value takes you in front of that plane, and a negative coordinate takes you behind the Y plane, behind the YZ plane. But X has to be 0 if we're on that plane. And since X is equal to 0, then I can simplify this equation to just Y plus Z equals 4. And I can simplify this equation to Y minus 3Z is equal to 8. And that's two equations and two unknowns, and we know how to solve that. Since both of these equations have a single y in them, I'm going to solve this by subtracting. Y minus y is 0. Z minus negative 3z is 4z. And 4 minus 8 is negative 4. And so z is equal to negative 1. And since z is equal to negative 1 and y plus z is equal to 4, then y is equal to 5. And so I didn't draw this correctly because the z coordinate is actually below the xy plane, not above it. But the point of intersection is x is 0 because it's on the yz plane, and y is 5, and z is negative 1. Okay? All right. So now that we can find intersection points and things like that, how do we find the distance from a point to a plane? Okay? So I have this plane here, and I have this point S, and I would like to know this distance. Okay? Well, again, if I knew what this point was, it would be easy. I could just use the distance formula. But chances are I won't know what that point is. But I can find any point P that's on the plane, calculate the vector from P to S, okay, and then take that vector and project it onto the normal vector. Remember that this distance is the same direction as the normal vector. And that will give us the distance that we want. That's the idea. Okay? This time, we get the leg of the triangle we want to by doing the projection. We don't have to do an extra step with the Pythagorean theorem. So if we want the distance from the point 113 to the plane 2x plus 6y plus 3z equals 12, I need a point P on the plane. Well, there are a lot of ways of finding a point on a plane, but an easy way would be to just go ahead and set x and y equal to 0, and then see what the z-coordinate has to be to make this equation true. So 2 times 0 plus 6 times 0 plus 3 times 4 is 12. This just happens to be the z-intercept. Any point on the plane is fine, but the z-intercept is easy to calculate. Set x and y equal to 0, and then find out what the z-coordinate is. So we have this plane. It crosses the z-axis at 0, 0, 4. And we have this other point, 1, 1, 3. All right, the vector from P to S this vector here is, I start at P, I end at S, it's 1 and 1 and negative 1. 0 to 1, 0 to 1, both of those are positive 1, but 4 to 3 is negative 1. The normal vector is this vector here. The normal vector is 2, 6, 3. And that's the vector that comes straight out of the plane in a perpendicular direction. It may not be exactly the right length that we want. It might be a little too short, or it might be way too long. But it has the right direction here. But if I project PS onto the normal vector, then I'll get the distance that I want. So the component projection, the scalar projection of V onto N, that's the dot product of both vectors divided by the magnitude of the one we're projecting onto, is, well, let's see, the dot product is going to be 2 plus 6, that's 8. 8 plus negative 3 is 5. The magnitude of N is the square root of 4 plus 36 plus 9. That's the square root of 49, which is 7. And so the distance from S to the plane is 5/7. All right. The next couple of slides walk us through this. We need to find any point on the plane. One easy way to do this is to set all but one of the variables equal to 0 and solve for the last one. So we don't have to use x and y. We could have used x and z or y and z, but pick a point on the plane. And then that gives us the vector from that point to S. Then we know what the normal vector is. It's 2, 6, 3, because those come from the coefficients on the left side. And then the dot product over the magnitude of the normal vector gives us 5 on top and 7 on the bottom. Okay? So just summarizing, the distance from a point to a plane is the dot product of a vector from a point on a plane to the point we're finding with the normal vector divided by the magnitude of the normal vector. That just summarizes what we did on the previous slides. One more topic and we're going to wrap up. If I have two planes, and again, this is the thing that's hard for me to draw. It's one of many things that's hard for me to draw. I want to find the angle between those two planes. Well, the angle between the two planes is the same as the angle between the normal vectors on the planes. That is, I have these two planes. The normal vector is a vector that's perpendicular to this plane. So this plane turned 90 degrees. And then the normal vector here is also turned 90 degrees. So whatever angle they make should be the same as the angle of the original vector planes, just turn 90 degrees. If both of them are turned 90 degrees, the angle doesn't change. And we know how to find the angle between two vectors. It's the dot product of the vectors divided by both magnitudes. Divided by just one magnitude gives us a projection. Divided by both magnitudes gives us an angle, or actually gives us a cosine. And then we have to do the inverse cosine to get the angle. Okay? So let's find the angle between these two planes. 3x minus 6y minus 2z equals 15. And 2x plus y minus 2z is equal to 5. So we'll take the dot product of the two vectors. That's 3 times 2 is 6. 6 times negative 1 is negative 6. 6 minus 6 is 0. Those cancel. And then negative 2 times negative 2 is 4. And then we take the product of their magnitudes. The magnitude of this vector is 7. It's the square root of 9 plus 36 plus 4 is the square root of 49. The magnitude of this vector is 3. It's the square root of 4 plus 1 plus 4 is the square root of 9. And so 7 times 3 is 21. And then when we take the inverse cosine of that, we get about 79 degrees. Okay? All right. Thanks for watching. We'll see you next time.